Hello, I'm Shirley Dulcey from the New England QRP Club, and today I'm going to talk about how you can test your transmitter using low-cost equipment. Now, one of the reasons this is so important to me is that as a QRP operator, I do most of my operation from the field. I live in a small urban lot, which really doesn't have space for HF antennas, and the ambient electronic noise level, both from my own house and the neighboring houses, and the LED streetlights and everything else, is so high that it's nearly impossible to hear anything on the HF bands. So I spend my time at home building and then take my gear out into the field and operate it. Now, as a builder, it's important to me to know that my equipment complies with FCC regulations, which restrict the amount of power that we can produce at frequencies other than the intended one. And these rules have become more restrictive over time as the state of the art has improved. Many
Finding
older
problems with
published
large
designs can no longer be
harmonics and
built as
out-of-band
published because they
spurs.
don't comply with
We'll
current
also want to
regulations. For many years, the test equipment required to fully test radio was far too expensive for most hams. That has now changed. You can do these tests with under $150 of new to you equipment, plus some things that you probably already own.
the actual transmitted signal in more detail. For that, we will use a software-defined receiver with a spectrum display. The minimum bandwidth that can be detected by the TinySA is 2.4 kilohertz, so it's not suitable for this part of the testing. Many SDR models are suitable, and it's likely you already have one. Some are standalone, others connect to your computer and display the spectrum there. The SDR cannot be part of the transmitter being tested. If that's your only rig, you're going to need another. Here's a list of some suitable SDRs. This is not an exhaustive list. The final piece of the puzzle is attenuation. You're going to be feeding the output of your transmitter directly into your spectrum analyzer or SDR. Unless you're testing a very low power transmitter, the transmitter produces far too much power, so you'll need a way to reduce it to a level that's safe for your test equipment. I'm going to have to spend a minute on math. It won't be too painful. The unit that's used to measure the signal level into test gear is dBm. That's decibels relative to a level of 1 milliwatt, which is 0 dBm. Decibels are a logarithmic scale. An increase of 3 dB is doubling of power. An increase of 10 dB is an increase of 10 times. 20 dB is 100 times the original power, and so on. A decrease of 10 dB is a reduction to 1/10 the original power. We can use an attenuator or multiple attenuators in series to reduce the output of your transmitter to a safe level for your test equipment. The first attenuator in the chain needs to be able to handle the full power output of your transmitter. The later attenuators in the chain only have to be able to handle the reduced amount of power that comes out of the first one. Calculating the total attenuation of two or more attenuators is easy. Just add the numbers. That's why we use a logarithmic unit to measure power. It's easy to see that at work in a step attenuator. The total attenuation is the sum of all the sections that you activate. Here are some important power levels expressed in dBm. The maximum input power to the TinySA is plus 10 dBm, but the optimum input power is lower, as that amount of power going into the TinySA can cause distortion that will affect your test results. Your SDR can probably also accept a plus 10 dBm signal without damage, but again, the optimum level is lower. A good target for these tests is a signal between minus 30 dBm, which is 1 microwatt, and minus 20 dBm, which is 10 microwatts. The TinySA will turn on its internal attenuator if the input is above minus 20 dBm. All of these numbers are large compared to the smallest signal your receiver can detect, which is minus 100 dBm or less. The most flexible way to get to a safe power level is to use a fixed attenuator that can handle your full transmitter power, plus a step attenuator to reduce the signal further to the optimum level for your test equipment. But you can also use a combination of fixed attenuators or a single unit if you can find one that's just the right size. Attenuators are expensive if you buy them new. You can find them at much more attractive prices if you buy them at a hamfest. You can also sometimes find them on eBay, and there are some kits you can build. Here are a couple of examples of attenuators. The two on the left are two lab-grade attenuators, both of which I acquired, surplus. The one on the top is the one that we'll be using later for the tests. The one on the right is a kit step attenuator that was published in QST magazine in September 1982. And I put that one there partly as an example showing how an attenuator works. You can see there are multiple sections of resistors. There's a pi network of resistors that is, say, one in series with the signal, and the other two shunting signal to ground. The sections are separated with PC board barriers to isolate them from each other. If you look carefully at the picture, you'll notice something. There are no resistors in the 20 dB stages. Those stages don't work. There is no output if they're turned on. I will install suitable resistors in the future to make it fully functional, but it was more interesting to show this way as an example of why you need to check your flea market purchases. So here is a 30 dB 20 watt fixed attenuator, looked at from two angles. Okay. This attenuator is non-directional. You can hook it up in the circuit either way and it will handle its full power. Here's an example of a 20 dB 150 watt fixed attenuator. This one is directional. It's important to put the transmitter signal into the end that's labeled input, because there are multiple stages inside this, and only that first one can handle the full 150 watts. Now, if I test a 100 watt transmitter, this single attenuator would not be enough to make things safe for my step attenuator, because if you put 100 watts into it, 20 dB of attenuation, you're still getting 1 watt out. That's too much for the step attenuator. So I would use this along with my 30 dB fixed attenuator to get us into the right range. An alternative to the high-power fixed attenuator is a resistive tap. Instead of attenuating in a beefy attenuator, you rely on a dummy load that you already have to dissipate most of the power. The resistive tap dissipates a small amount of power, so it can be built with 1 watt resistors for use with a 100 watt transmitter. One caveat is that the spectrum analyzer or receiver is part of the circuit and affects the total attenuation. The resistive tap designs are based on 50 ohm impedance, which is fine for analyzers, but it may not give you the right result if you use a receiver, because the input impedance of receivers is not always 50 ohms. So here's an example of what a resistive tap looks like on the inside. You can see there are 3 resistors there adding up to about 2,500 ohms. It's actually 2460 to 3 820 ohm resistors. And then there's a 50 ohm resistor at the end that's in parallel with the load, which is either the spectrum analyzer or the SDR. Okay, so we're about ready to do some output spectrum tests using the TinySA. So we're going to have a look at how you set up to do that. So we're going to configure a couple of things on the TinySA and use its automatic settings for the rest. We're only testing levels relative to the carrier, so we don't need to do anything else. The main thing we'll be setting is a suitable frequency range. We want to be able to see multiple harmonics as well as looking at lower frequencies to make sure there are no out-of-band spurs. All of the tests shown in this presentation are using 40-meter transmitters. They're used in the CW portion of the band in the vicinity of 7.040 megahertz because the tuning 2 is crystal controlled. The two-tone test of sideband break, which you'll see at the end, was done at 7.2 megahertz in the sideband portion of the 40-meter band. I only changed the start and end of the frequency range. Start is set to 0 megahertz, the end is set to 50 megahertz. The TinySA has performance limitations below 1 megahertz. The first part of the sweep is not completely accurate, but I found it easier to read the display starting there. The end frequency of 50 megahertz allows us to see up to the 7th harmonic of the carrier. So, here we see the setup. I press tap to bring up the menu, and then tap frequency, and then start. 0M means 0 megahertz. Tap again, hit the stop frequency, this time 50M 50 megahertz. And there we are. Our TinySA is now ready to read our spectrum. There are many more settings available. You can set the frequency range by setting a center frequency in a range rather than start and stop. You can set the input attenuation manually. You can set the amount of attenuation that precedes the TinySA so it will display actual power levels. And you can store your favorite settings for future tests. I kept things simple here to show you can do useful measurements without fussing with all of that. And because the focus of this video is the testing procedure, not the details of the TinySA. You can learn more about the available options at the TinySA wiki. For testing in another band, you'll want a different frequency range. Going up to the 7th harmonic is a good starting point. Here's a table of suitable values. So, now we're going to see me set up the TinySA along with the other equipment necessary. Going from left to right, you can see the TinySA, the step attenuator, the fixed attenuator behind it. The radio under test this time is QRP Labs QCX Plus. That's what you see from the back there. And finally, there's a power distribution box from Soda Beams and an LFP battery.
Okay, next I'm going to show you how all the test stuff is going to fit together. First, battery, 2, distribution box, cable, for the radio under testing.
I made a mistake here, tossing that cable aside that I actually needed. I'll get it back. So, you see the output of the transmitter is going into the fixed attenuator. That then goes into the step attenuator. Alright, so now we're ready to do some tests. So first radio I'm going to test is my Elecraft K2. Now, you may be wondering, I set up the QCX Plus first, but we actually tested the K2 first. So the output power of the K2 in this test was 5 watts, which is plus 37 dBm. I used 30 dB of attenuation in the step attenuator, plus the fixed 30 dB attenuator, adding up to 60 dB, and reducing the 5-watt output to 5 microwatts, which is minus 23 dBm. The highest peak in the spectrum analysis is the fundamental. The second harmonic can be seen at least minus 45 dB. Actually, that was from an earlier test at the 8-watt power level. At this power level, it's closer to minus 50 dB. It's the only harmonic visible. So there we have the radio, and you can see the spectrum display. The biggest pip there is the fundamental. The next pip, another 7 megahertz over, is the second harmonic, which again is down about 50 dB here. And we see no other harmonics. This is an excellent spectrum result. This radio is compliant with FCC requirements with room to spare. Next, I'm going to test the QRP Labs QCX Plus. This radio produces about 4 watts output. Once again, I used 30 dB of attenuation in the step attenuator. Now, the highest peak here is the fundamental, and then the second harmonic can be seen at minus 47 dBm, also compliant. So there we have that. Now, just so you don't think everything will pass, here's a spectrum display from a rig that is not compliant. This is the NorCal version of the Tuna Tin 2. It used toroids in place of the no longer available Radio Shack bar inductors. This is a milliwatt rig, so I only used 20 dB on the step attenuator. This brought it down to about the same power level as the other two radios. The second through fifth harmonics and the seventh harmonic are visible. The worst is the third harmonic, which is down only about 34 dB. The fourth harmonic is down about 44 dB. This rig is compliant with the regulations in effect when it was built and can be legally operated, but a duplicate built now would not comply and would require the addition of an external filter or modifications to the circuit to be used legally. Now, although I could use this rig as it stands legally, I don't really recommend it. It's not consistent with best practices, so I would use this with additional filtering. So here we go. Again, you can see the biggest peak is once again the fundamental, and you can see harmonics 2 through 5 and 7 right over near the right edge of the display. The sixth harmonic is not visible below the noise level. And the noise level is about 65 or so dB below the carrier. So, there may be some sixth harmonic energy, but it's lower than that. Once again, the TinySA has a minimum receive bandwidth of 2.4 kilohertz. That's the smallest slice of spectrum it can resolve. It's not suitable for looking at problems close to the carrier, where we're typically looking for narrowband problems that may be only tens of hertz wide or something like that. So now we're going to turn to a software-defined receiver. I'm using a Hobby PCB RS HFIQ transceiver, which I'm only using as a receiver here, and a Pi SDR IQ Plus interface from SV1EIA. This combination covers all the HF bands through 30 megahertz and offers a high dynamic range. The screenshots show a version of Power SDR from Flex Radio that has been modified to work with the RSHFIQ and Pi SDR IQ Plus. I'm going to show a series of spectrum checks, first of the transmitter off, and then with the step attenuator set in 10 dB steps from 60 to 20 dB of attenuation. The reason for this is to show how it's important to operate your SDR within its dynamic range so that you're not seeing spurs generated as intermodulation products in the receiver. So, in all of these, we see a spur at 7.048 megahertz, 8 kilohertz above the carrier. In the later checks, yes. The elevated area of noise at 7.032 megahertz is the zero crossing of the quadrature sampling detector. It is normal for a QSD SDR. You know, you don't normally receive that portion of the spectrum from it, but if your SDR has a panoramic display, you will see the noise hump there, as we do. Even with no signal, you can see that big noise hump there at the zero crossing. And there's another spur about that's about 8 kilohertz above the carrier. And we can see another smaller one about 16 kilohertz above the carrier. Those are artifacts in the receiver because you see we're not even supplying any RF to it yet. Okay, so here is what we see when we first add RF. The main thing we see here is the carrier, which is currently at minus 50 dBm, because of the amount of attenuation we're using. And the rest of the spectrum has not changed noticeably. So, the noise floor there is about 80 dB below the carrier. So we have, an almost spurious free dynamic range here of at least 80 dB. This is a pretty good receiver. Okay, now we've taken the attenuation down to 50 dB. So the carrier is now at minus 40, dBm. But we've noticed something happen. A bit to the right of that spur that was already there, there's another spur that has just popped up. That's an intermodulation product in the receiver, which we will see as we go to the next one. Now you'll notice how that spur, when we went down to 40 dB of attenuation, rose much more quickly than the carrier did. The carrier only went up about 10 dB to minus 30 dBm, but that spur increased by almost 20 dB. That's an indication that it's a third order intermodulation product. When we decrease the attenuation yet again to 30 dB, again we see the carrier has gone up, but that spur jumped up another 20 dB. It's gotten even bigger. And if you look further to the right, you'll notice another new spur, which is the farthest one out, which suddenly jumped up by a whole bunch. That is a fifth order intermodulation product, which we'll see in this final slide. Okay, here we've basically driven this receiver into overload. The carrier is now at about minus 10 dBm. That third order product has jumped up another whole bunch. The fifth order product jumped up even faster. That's the indication that it's a fifth order product. We see some additional spurs over on the left side of the display. And finally, the whole noise floor near the carrier has now elevated a lot. This is an indication that we're probably driving this SDR into overload, and it would not work well on the bands if you had a signal this strong coming into it. So, one more test remains, which is the two-tone test we use to find intermodulation issues in sideband transmitters. Two of the breaks I use here are CW only, and I don't currently have a way to get audio into the K2 other than the microphone. So I'm going to do this test with a brand new radio to me, the SBitX. The SBitX has a built-in two-tone mode, but most of you won't have one, so I'm instead going to show how you can use your computer to generate the tones. You'll need an audio interface to your computer, the same kind that you use to send digital modes. The SBitX has a standard 1/8 jack for its microphone input, so a simple audio cable will suffice for getting audio into it. Watch out for ground loops. If you power things from wall power, I'm using batteries. A separate linear amplifier is normally tested with two RF signal generators, but to test an SSB transmitter, we put in two audio tones because we want to see the effects of the entire transmitter chain. The usual tones are 700 Hz and 1900 Hz. I'm using an online tone generator, the aptly named onlinetonegenerator.com. It only generates one tone at a time, but I ran 2 copies of it in 2 browser tabs. The two-tone spectrum of the S-Bidex is very asymmetrical, with the third-order product on one side much higher than the other. Here's the graph, and you can also see that it's not a very clean two-tone spectrum. I'm not sure whether that's a problem in the radio or a problem in my test procedure, but you can at least see the 2 peaks in the middle are the 2 tones, and then you can see the third order products on either side. The one on the left side is down about 30 dB from the tone peaks, which is 36 dB below PP. The third order product on the right side is down another 10 dB below that, which is unusual. Most radios you'll see a fairly symmetrical result there. So I think that something is a bit off in the setup of this radio, which takes further investigation. So finally, some references. There were some ARRL articles on step attenuators that you can view or download if you're an ARRL member. They're listed here. And finally, here are some online links to some of the things I talked about in this presentation. So, time for questions and answers, starting now.
Okay, hello. Okay, our first question was from Jeffrey, WB8REI, and he asked, how about using an RF sampler? Well, as it happens, that was already addressed a little bit later in the video when I showed the resistive tap. That's one form of RF sampler that you can use. Some dummy loads. Oops. Okay, let me continue. Okay, audience, let me know, are you hearing me? If you're not hearing me, then Ron will have to address some issues and we'll start over from there. But meanwhile, I'll continue with my answer to Jeffrey. Also, some dummy loads have an RF sampler built in. The classic Cantenna, for example, has one. You can use that output. Now, that will not work for absolute measurements because you don't know how much attenuation that sampling output has. But for the relative measurements we're doing here, it will work just fine. You may also need the step attenuator to get things down to the right level for your analyzer, but you should not need the fixed attenuators that I showed in my presentation. Okay, so anyway, I haven't heard anything from the audience yet about not hearing me, so I will continue. Okay, John, K2CIB asked, what about taking measurement off air using a small antenna on the device and the transmitter at low power into a dummy load? Well, you could do that, but you probably won't get as clean a result because the antenna on the device will not only pick up the signal from your radio, it will also pick up all the RF noise around you. And if you live in a typical environment that most of us do nowadays, there's going to be quite a bit of RF noise there that the analyzer is going to pick up. And that will make your results less accurate than they could be. That's why we're using direct cables, shielded cables, from the transmitter all the way to the analyzer, through the attenuators, because we're keeping out as much external noise as possible. Now, if you live in a really quiet environment, if you're out in the country and you can pull the big red switch on your house and turn off your Ethernet and all your electronic gadgets, you might be able to get a good result with an antenna. Okay, and finally, George, WB6YZZ asks, do you trust the accuracy of the VNA across its spectra? Well, the short answer is yes. People have tested the TinySA, through the entire HF spectrum, and it has worked well. It's flat within a dB or two across the entire low range. Now, something I forgot to explain in the presentation was the difference between the low and the high range of the TinySA. The low, there are two separate inputs, low and high. The low input measures up to 300 megahertz, and the high input measures up to 960 megahertz, but it also has a floor at 240 megahertz. All of the tests I was doing here were using the low frequency input, which is more flexible of the two. Also it uses a simulated sine wave oscillator rather than the square wave oscillator in the high range, so it will produce a cleaner result. And unfortunately, that means that using low input, you're pretty much limited to testing HF gear. You could look at the third harmonic of, you could look at, up to the fourth harmonic of a 6-meter rig. Once you're up to 2 meters or higher, you're going to have to use the high range, which is, less capable. Honestly, if VHF and UHF is your primary interest, you probably want to wait for a different instrument. There are things under development that would be better suited to testing those frequencies. Okay, yes, we have another question here from Montgomery, VA7MMW. Okay, so what signal input source you use to test? A transceiver? Is it a CW tone generated by the transceiver? Yes, for the harmonic testing, that is exactly what we were using. Transmitters were set to CW mode. Some of them were CW only, and tested that. Now at the end, I also showed the two-tone test, where you're using the transmitter in sideband mode and sending audio tones into it. Okay, for testing a power amplifier, I've not addressed that. One problem there is that you do need a very clean signal source to feed a power amplifier, because otherwise harmonics from the signal source might also be amplified by the power amplifier, and that would make the result less accurate. Now, what you could use is a QRP transmitter or transceiver, along with additional low-pass filtering. Add a separate external low-pass filter between the QRP transmitter and the power amplifier. That should bring harmonics down by, an additional, probably an additional 30 dB or so. So instead of minus 40, dB from, carrier, you'll be at minus 70 dB or so. And so any amplification of those harmonics will be at a low enough level that it's not likely to interfere with your tests. Okay, now there's another question here. It says, can you use a QRP transceiver to generate the 8H07T test signal? I don't understand that question. If you could clarify that in the chat, I will come back to that one. Okay, and then 3 says, is the input CW signal generated by a transceiver clean enough for good testing? Yeah. And if you're testing a power amp, how do you reconcile a non-perfect input signal source containing harmonics with the output spectrum? Well, as I said, typically the signal from a transceiver will not be clean enough to test a power amplifier separately. What I would do, again, is add additional filtering between the signal source and the power amplifier, and that should make the signal clean enough for a good test. Okay. Now, Wade, VA3NCA asks, could you measure the attenuation from an RF tap-style dummy load with TinySA? Would the attenuation be variable and reliable? Well, yes, you can. The TinySA does accurately display absolute signal levels. So if you know the power level of your transceiver, which you measure, with your watt meter, and then you measure, you look at the signal coming into the TinySA, you could calculate how much attenuation you're getting, from the dummy load. Now, again, it's possible that signal would be too large if you put a step attenuator in between the TinySA and the transmitter. You would just add the additional attenuation from the step attenuation, the step attenuator into your calculation. Okay. Now, Jeffrey WB8REI asks, so often you see folks hold an HT up to a spectrum analyzer to see how spectrally clean its output is. Is this just a rough test? And if so, is it a reliable and accurate test? Well, the answer is it depends. What is the environment? Now, I said that doing that kind of testing on HF is going to produce poor results because most of our environments are very dirty on HF. There is a lot of noise on HF. It comes from switching power supplies and all of your electronic gadgets. It comes from your LED light bulbs. It comes from radiated signal, from the Ethernet network that you might have in your house, and so on. Now, when you get up to VHF, the ambient noise level is lower. So the result you get by holding the HT up to the spectrum analyzer is going to be better than the result you get from the TinySA, testing on HF. But there's still a problem there, which is that you've now introduced, more variables into the equation, which is the bandwidth of the antenna on the HT and bandwidth of the antenna on the spectrum analyzer. These may not be flat across the spectrum. And so the harmonics may not be as effectively radiated because the antenna isn't a very good antenna on the second harmonic or the third harmonic or whatever. And similarly, whatever antenna is on the spectrum analyzer may not be flat. And that, again, is going to affect your results. So that's just a rough test. The best way is, again, to run the signal directly into the analyzer. If you've ever been to the ARL booth at certain hamfests where they test HTs, you'll find out that that's exactly what they do. They attach a cable to the top of your HT, and that cable goes into some attenuators, very much like the ones I was using, and then goes into their spectrum analyzer, which in their case is, a fancy, lab grade, Rigel or HP or something, and that's how they show you the spectrum. So the rough test, holding the thing up is useful, and it will find egregious problems. But if you want a really reliable result, you will cable directly in. Okay. Now, if there aren't any more questions, I would also like to address one more thing before I hang up, which is, what are the standards? Well, here in the US, the standard on the HF bands, as they bands below 50 megahertz, is that all spurious radiation has to be at least 43 decibels below the level of the carrier. This is pretty much independent of power level, until you get down to microwatt radios. So that's what you have to comply with. Now, back in the 70s, it was only, 30 dB, which was a much easier standard to meet. So some of those older designs won't comply with current standards. When you get above 50 megahertz, in the VHF and UHF bands, the standard is 60 dB down. This is a much more difficult standard to achieve. Now, you do get a little bit of grace in that it's 60 dB below 25 watts. So it's either 60 dB below whatever your actual power level is, or 60 dB below 25 watts, whichever number is, smaller. So for example, if you test a 5-watt HT, the harmonics only have to be 53 dB below the carrier, because there's a 7 dB difference between the 25-watt and 5-watt power levels. But that's still 10 dB more stringent than the standard in HF, which makes it more difficult to achieve. Okay, so unless anybody has any last-minute questions, I'm going to end things here.